Olá a todos, sejam muito bem-vindos, um bom dia a todos. Esse é o nosso quarto dia do WebMedia já, espero que vocês tenham aproveitado bastante todo o evento, e ainda tem muita coisa para acontecer ainda. Eu estou aqui com o meu querido amigo Roberto Gerson, que eu convidei aqui para participar comigo como co-chair desse Keynote. Eu comecei em português para dar oi para vocês, mas eu vou precisar chavear para inglês, porque a nossa apresentadora hoje é apresentadora internacional. So I will begin to say that I'm truly happy to be here. Every year, WebMedia bring an international researcher to be a keynote here in WebMedia in order to bring some new topics or even appoint some new challenges and new research directions that the web media community can focus on. And in this year, we invited Professor Laura De Toni from UCL, and we are deeply honored that she accepted our invitation. And I also invited Roberto to share with me. The idea is that both of us will make questions to her, and we are also guiding the questions from the audience to her. And I hope that it will be a very fluid conversation. I expect that everyone can make the questions in the chat. Don't need to wait for the end of the presentation to make the questions. So feel free to make questions, even in Portuguese. If you want to make a question in Portuguese, you can translate to her. So I need to introduce Laura. Laura is professor at the University College London, received her PhD in electrical engineering from University of Bologna, Italy. She also was a postdoc at EPFL in Switzerland and was also a postdoc in University of California. She co-authored high-impact publications and has involved in conference organizations like MMCs, ECME from EEE. Her major contributions are in the field of multimedia processing. In particular, in multimedia processing, she has invented some patents in low video streaming, low bandwidth video streaming. She also contributed to large-scale signal processing for machine learning, graph signal processing, decision-making strategy under uncertainty. So that is a long CV that I will not detail here, but we are very happy to receive Laura here. So without no more delays, I invite Laura to make her presentation. And Laura, feel free your stage is yours.
Thank you, Alan. Thanks for inviting me, and glad to see you and Roberto here. I can directly start, I guess. So now you should be able to see the presentation. I'll take it as a yes.
Yes.
Okay, excellent. Okay, so thanks again for the very flattering invitation. It's an honor for me to be here. The title today is a little bit a mix about power of graphs in immersive communication. So I thought about the type of conference that is WebMedia, which is somehow both media but also web, and I felt that providing you an overview of the works that we do at UCL on immersive communication, but from a graph perspective, can help also, or could be interesting also for the people that are more related to web and not only media. So that's why also I try to take this perspective. Before starting, let me thank many people I worked with. Of course, my team in UCL, at least the ones that mainly work around graph and immersive communication, but also all the collaborators that we found along the ways, of course. And today, the talk will be, as I just mentioned, about immersive communication, but also graphs. I hope that I will convince you, as Alan would say, that I see graph everywhere, and there are really tools that can be very useful, both for classic graph methodology and for also graph signal processing tools. So I'm going to explain you a little bit more, but let me first motivate you.
So what we're seeing is a real-time.
sorry. Let me motivate you the overall topic that we focus on in our last team at UCL. So the overall idea is we have been witness a paradigm shift of how we consume the multimedia content. So in the past, we were passively receiving media content, for example, from TVs, right? But now we are generating, but most importantly, interacting with the content. So we really believe that we have seen now a new era in which the user has a key active role in how the content is consumed and generated. And that has changed completely the overall pipeline and the overall thinking at the pipeline of the coding and delivery streaming. And there are key new challenges due to this paradigm shift. For example, the first part is that there are new content, for example, spherical or volumetric, but there is new media format that needs to be processed. These new formats are usually large, so large volume of data that needs to be stored, delivered, and rendered and processed. At the same time, to make sure that users do feel fully immersed in this reality, so we consider both immersive reality, in which the user feel immersed in a virtual reality, or also augmented reality, right? In which we have external auxiliary objects that can augment the reality in which we live in. So in both cases, we want ultra-low delay in such a way that while we move in this augmented or virtual environment, we do have the content moving along with us. So we do feel fully immersed, right? And that, of course, is constrained by bandwidth limited resources. At the same time, since you might say that's okay, we have a large volume, we also want ultra-low delay, we can send everything. Well, that's not always possible because we have bandwidth limited resources, but we can maybe try to send to each user the content they could be interested in, or at least try to tailor each service to the user, but users are actively interacting with the content. So we have a big question mark that is around the uncertainty of the user. So what the user are going to display, how they are going to move within a virtual environment, how they're going to behave. That's something that is uncertain, and that creates a higher level of challenge. So today, I'm going to talk a little bit about the research we have been focusing this main uncertainty challenge. So it's the study that we have done about user behavior in virtual reality. But then I'm also going to show you some research advances in the second aspect of we have new media formats. Specifically, we're working on dynamic point cloud processing. So I'm going to talk a little bit about both of them, mainly to show you how we use also graph tools in this. And then I will conclude some open challenges and perspective. So let me tell you that first, to make sure that everybody is on board and everybody can get something home from today, I just would like to have a quick introduction to graphs for those that are not familiar with that. And then I will describe these two topics, behavioral study of interactive systems and point cloud processing, before concluding the talk. So let me go to introduction to graphs. So what are graphs? So graphs are a very efficient representation or way to represent any pairwise relation between two entities. So for example, you can also see a map, and you can see bridges in the map, and you can then see in this simplified version, and this can be represented as a graph. For example, bridges can be nodes on a graph, and the edges can be representing the water flow that connects the graph, right? So you can really think any irregular structure that can be represented as a graph. You can have, for example, geographic maps, network, traffic networks, social networks, brain networks. We can also have point clouds that I will show you later. So all these are irregular domains that, however, still have a very strong information related to the topological structure that they have. So the question is how to leverage on this topological structure, and using graph tools can actually be a solution to that. Why or what can you do with that? Well, there is a recent field that has been growing massively now that try to adapt machine learning tools to graph data structure. So the type of network that I showed you before, for example, traffic or even brain signals or healthcare signals, can actually be seen as topological structure, so some nodes and some data, some nodes in a graph. But then we can have some signals on these nodes, right? So we can see this signal as a graph data structure. So they have a temporal evolution, but they sit on specific nodes on a graph, right? And there are tools that can actually be used to learn behavior of these graph data structures. For example, we can have graph level classification. So we can classify whether the patient has a condition or not. We can have node level classification to understand, for example, the label of each voters in this simple example. Or we can also use this structured data to then infer possible clustering. That it's one of the aspects that we actually use today in the talk. Or, for example, highly important, we can actually infer the topological information that we have. So we might have some data, and we would like to understand the actual relationship that is underneath this data. That, for example, can go into protein-to-protein interaction, but sometimes can also be used in some aspect of point clouds and volumetric content. So all these tools is what sometimes you refer as graph or GSP-based machine learning tools. For those that are interested, there is a review that we published recently that really tried to show these type of settings of a graph and a structure, a signal that lives on the graph, and how we can use this topological information to then perform machine learning tasks that I told you before. And to conclude this overview on graph, let me tell you where everything started. So this concept of signal on a graph is what you can refer also to graph signal processing. We have very good colleagues that started this field. And the idea is that you have nodes and edges that kind of represent some relationship that might exist between pairwise. And you also have some signals, so some features that can be positive or negative that live on the nodes. As we said before, for example, this can be the brain signal that we monitored before, can also be in the case of point clouds, RGB colors, so the features of each point in the point clouds, can really be any type of information that associated to a given node. And the idea is that we would like some tools that is able to capture the information that is in the data, but also in the geometry of this data. And what was interesting is that in the past, the researchers were able to create an association from the classical signal processing tools that we have seen in the past to more, let's say, modern graph signal processing tools. So as we thought before in the undergrad study, we saw the Fourier transform and inverse transform that allows you to go from time to frequency and from frequency to revert back to time. You can do the same in the graph components in which you have a signal in the vertex domain, so on the graph, but then you can revert into a spectral composition domain and then go back to the vertex domain, and that's by the graph Fourier transform. I will not give you the details here because it's outside the scope of today, but I just wanted to give you the very nice intuition that these tools allow you to still have low frequency and high frequency components that is still related to low frequency like DC components or very global structure across the graph. And high frequency components are really more the high frequency component we think in the signal processing, classical signal processing, so more localized information on the graph. And you can see your signal as a composition of this basis function. What is interesting is that also you can perform the classical tools that we have as a filtering and convolution on the graph. So you can think, for example, that you have a signal, you can convert it into the spectral domain, perform a filtering that it may be, we call it also generating kernel, that usually depends on the Laplacian of the graph. And then you can get out a filtered signal. And if you assume that each color represents the intensity of the signal on each node, here is the color map, you see that after the filtering, the signal is much more homogeneous. We call it smooth on the graph. And that's because you kind of perform a denoising, a smoothing signal on the graph. So it's really kind of the same analogy you had from the past that you can apply also here. And what I'm saying is that because the classical convolution that we have in the time domain, you can then also have it in the graph domain. And I will not go into the math, but for those that are familiar with geometric deep learning, this concept of spectral convolution is somehow where everything started, or at least is the originating point of that. And we can now think about graph convolutional network or graph neural network as a set of convolutional filtering, either in the vertex or in the spectral domain. So there are some key differences, but we can think these as the originating point of what we now have as deep learning on graph. And in part is what we use later on during the talk. So that's why I wanted to give you a quick overview. Also because I think it's a tool that is very useful for also people that are outside the multimedia field. And as a starting the take-home message, that's just the beginning. So introduction of graphs that are structured data that are everywhere. If you think about it, that really start to pop up in your mind in many applications. GSP is really kind of the originating field of trying to look at signal processing tools into this structure, irregular structure domain. And now there is a kind of really quite vast and active field of literature in that sense. Why I'm saying that? Well, let's go with the first part of the talk is let's see the advances that we have done in the behavioral study of interactive users in immersive communication. And let's see where graphs are here. So the first thing to say is that I mentioned that the main goal of this first part of the talk is to deal with the uncertainty that we have about the user. Specifically in a virtual reality environment, whether it's a single user or social VR, you do have key questions that you would like to answer. And actually it's the question that we try to answer with the work that I'm going to present you now. So one is, can we identify dominant behavior? So when users navigate in virtual reality, how do they navigate? Do they have common behavior? Are there key dominant patterns that exist? And can we quantify these similarities? Can we actually see that users tend to behave in the similar way despite the content? Or could we actually identify external factors that play a key role in this navigation? So these are all questions that we ask. And why we ask that is because, well, first, everything started from coding and streaming delivery and rendering optimization. So in the overall pipeline, the user has a key role in dominating the scene on what is going to display. So should the whole streaming pipeline, coding and streaming pipeline be tailored to that? Should be personalized to this behavior? And if yes, how do we know which behavior it is, right? So that's the starting point. Along the way, we realized that we had some discussion with psychologists because VR therapy with VR is also used in therapeutical approaches, and being able to quantify and assess the behavior of the user in that field is very important, and also can be used to measure engagement or some level of interaction in live performance scenes. So it's also, let's say, going beyond the simple optimization of the delivery chain. Why we need that? Well, let me give you an example. We have traditional metrics. Let's say we call it traditional, meaning more metrics that perform an average evaluation of the user behavior over time and space. For example, in this case, we have two types of user. Each of these points is a user navigating within an omnidirectional field. Here we see the 2D just because we have the projected version. And let me see if I can replay this again. But basically, the idea was that in these two scenarios, the scenario B have points that are much more going from one cluster to the other, while here they're more moving around one cluster. So the behavior is completely different. And yet, if you look at the average behavior, for example, heat map or average metrics like that, they tend to be similar, right? So you don't really spot this different behavior that, however, we would like to spot. So the classical methodology do not fully capture the behavior that we're interested in. And that's why we started to develop the user behavior analysis in VR streaming. So beyond the classical steps of experiments, collecting data, and pre-processing, we mainly worked on the user trajectory analysis. So can we look at where the user watch in virtual and augmented reality over time, and can we extrapolate information about the user in that sense? We do that both in the intra-user, so the single user but looking at different content to understand that there is a kind of possibility of profiling users. But we also do it inter-user behavior analysis. So if you have one content and we see all the user watching this content, what can we guess? What can we say about that? For example, can we understand what is the affinity, the similarity between the user? So now I'm only going to focus on this first inter-user behavior, also because it's the one where we use some graph clustering, so we keep the theme of the talk. If I have time, I will mention the intra-user behavior results. Let me tell you more what do I mean by navigation, similarity, and clustering. So our goal is given a spherical content. So I'm now in the classical 3 degree of freedom, where the user is at the center of a spherical content, maybe wearing headset and moving the head and moving the viewport that is displaying. So each of these color trajectory is actually the movement, is showing the center of the viewport that the user is displaying over time, right? So by looking at that, we would like to understand clusters of similar behavior, where for us, similar behavior, it means users that are really watching at the same content. So how do we do that? Is exactly what I just mentioned. So you have different viewports that are observed over time. Looking at the center of these viewports, we can then extrapolate a trajectory. If we then look at this center viewport trajectory for different users, you get these 3 trajectories, for example. So the first part is we are really interested in understanding when do users look at the same portion of content. Because, for example, we want to cluster them and perform some processing at the edge for this type of users, or for any other type of reasons that I'm going to explain later. So what we did is, okay, for example, let's assume that we have these 3 points, these 3 users. We can see them on a graph, okay? So each of these users is represented by the color. And we can see that here at the very beginning, user green and blue do have a similar viewport center. So they tend to display a good overlap. So they assume that they are watching at the same portion of content. Therefore, we create an edge, a link in the graph, and we assume that neighboring nodes are defined as such if they look at the same portion of content. For example, in this other example, in which we look at this temporal aspect, we see that now the blue user is actually in good overlap in terms of displaying content with the red one, but not with the green, right? So we just So we basically look at the graph as a tool to understand this concept of user similarity. So are users watching at the same content? If yes, they should be a neighbor on the graph. So the idea is that we want to have a construction of this graph, which is not that straightforward, as I mentioned, and I'm going to tell you a little bit now why, but that's the first step. And once we have that, as I mentioned before, we are interested in having that. We want to identify users that are watching all at the same portion of content. So we're really interested in defining cliques in which you see nodes are all neighbors of themselves. So they're all connected between themselves. And why we want that? For the reason that I just mentioned. For example, we would like to say, if I have to deliver specific content and high quality to that cluster of user, because maybe the delivery network is such that it allows me to perform that, or to code for some key main dominant behaviors, which one are these? So we really want to define these as the ones for which users do look exactly at the same portion. So we then apply some maximum click clustering that we use to identify these main dominant behaviors. One thing to say is, okay, we propose a first methodology. So that's a metric that we proposed with my PhD student Silvia a while back now to study user similarity. So it's basically consisting of 2 steps. Step 1 is let's create this concept of graph. So there are 2 main limitations. First is that we cannot simply say that for all users, we look at the pairwise overlap on the viewport and we just say yes or no, their neighbor, and we create a link, because that's highly inefficient. So we had to do some further study to understand how we can rely on geodesic distance between 2 users looking at the jetty distance of between the viewport centers to then be able to assume that they are neighbor or not. Just to give you an intuition, if you only look at the center of two viewports, you miss the rotation bit. So the overlap can be quite different depending on what is the actual rotation. So that's why we have to consider a threshold-based geodesic distance. Second aspect is that actually we look at trajectories. So we would like to have that two nodes are neighboring if the overlap is consistent within a given time window. So that's also a second step that we face to construct this graph. But once you face that, then you can have that graph. And the second step is to consider some state-of-the-art click-based clustering. And especially we consider the one that try to achieve the maximum, so the most populated clustering that we can have. And that's because we're really interested in also understand what is a dominant behavior. So for example, if you want to optimize your coding, you may want to do it following these dominant behaviors that the user have within the spherical content. So that's a little bit the approach. So we build the clicks, and that visually gives you already intuition, but also we wanted to have some quantitative metrics for the reason I mentioned before. So we kind of translate that into affinity matrix. That is simply, if you have C clusters, each of that with WI number of user, and XI is the percentage of user within a given cluster, we have a weighted sum of this number of users. So that's the affinity matrix that we got. And just let me give you some high-level results. So if you look at some classical K-mean or spectral clustering, in this case, we have a spectral clustering result, and we compare it with the click. Let me tell you what you say here. So here you have your spherical content projected on the planar, and each of these lines is a trajectory of the center of the viewport for one given user. If user belong to the same content, the line will be actually the star points here, would be with the same color. What you observe is that you have some user mainly playing around at the center, so not moving drastically. And then we have some outlier, for example, this orange person that is actually quite moving around the spherical content, the equatorial content, and also the green one, right? So you really want to understand dominant behavior against outlier behavior. And that's something that you don't get from the other type of clustering. In part, it's also because of the click imposition that we do have. So we really want to identify meaningful cluster. That's also useful because, for example, you can also perform some pre-processing or pre-analysis of your content. For example, in this case, you have a roller coaster video. Here you have time. Here you have 59, I think, users that you observe in terms of trajectory. So this kind of data set that tells you the quaternion of the user moving over time. And the color code is simply telling you the number of users in the cluster of that given user. So what is interesting is that at the beginning, all the users are wandering around. That's very typical in VR settings. And you can see that there is really a blue area. So there are a lot of clusters with few users. So there is no one dominant behavior. However, some moment in time, it's interesting because you can really spot some red lines that it means that there is one big cluster. So it's a kind of something happening in the content and most of the users are kind of following the same behavior. So that's, for example, very interesting because if you want to predict your user behavior, you know that here maybe might be challenging, but in the red area might be more promising to actually predict the user and perform maybe a viewport adaptation logic. So it can be useful also to understand how to act. Another study, I will not have too much time now, but another study that it's also interesting is how this behavior is affected by content, but also by the displaying video. So that's something that we did in this second work that we looked at, in which we consider also a data campaign to collect the trajectory of user behavior with different devices, so with HMD, laptop, and tablet. And somehow we saw that HMD has the lowest speed across devices and video categories. So it was really interesting to see how the interactivity of the user and the similarity between the user that can be translated as a sort of engagement can be affected by the displaying devices. So that's a little bit the first part of the study we did. And somehow as a take-home message that I may want to give you as results of this analysis is that As you can expect, when there is no main focus of attention, users do not have a strong affinity. So similarity is not that high, and you tend to have more blue areas, for example, of the plot that we saw before. At the same time, you do have stronger affinity in the case of one focus of attention. And also the device does affect your affinity level, especially HMD leads to quite similar navigation among users, but slower. So that's kind of interesting reflection that you could take. And in the journal that I mentioned before about the different devices, we really try to highlight key take-home messages of the type of behavior that we observed during the study. That first part was mainly for 3D of 3 degree of freedom. So when you are seated at the center of the sphere and they move your head, of course, there is a lot of research going on 6 degree of freedom, right? So for example, if I'm observing an object, whether in a virtual or augmented reality, but whether I'm observing an object and I'm looking from an outward position, and I can also move my body, not only the head. So there is not only the rotation of the head, but there is also the movement of the person in the physical space. So I can watch this object from a closer position or from a more far away position, right? So the question is, how does it work, the study that we have observed so far in this 6 degree of freedom environment, and how it is affected by the fact that we do have a higher level of freedom. So that's a very initial results. We are in the process of submitting now the journal, so more to come, let's say. But I can give you a quick idea and an understanding on why we need to go beyond the study that we have done so far. So if you look at this object, this figure in which you have a volumetric object, you might have the orange user moving over time, so physically moving in this space with position xi. And then you can have xj, so this green user moving with this other position over time. So what you have now is you do have the x position, physical position of the user in the space, and the center of kind of the viewport that it displays projected on the object, right? So currently we were only looking at this position till now in the 3 degree of freedom, but that's not sufficient anymore. An example to show you why is this result. So let me explain it to you. If you have a point cloud object here, you might have this as the position of a user in a given time moment, and the same color, and the colors is given to user, same color is given to user in the same cluster. So we look at the user, we look at where they're looking at, we look at the positions, and if user look at the same portion of the point cloud, or at least with at least an 85%, 75% overlap at the same displaying overlap, then they would be in the same cluster. So that's something that we do as a ground truth. So we really look at all the users in a given time, where they look at, we evaluate the viewport, we measure the overlap. If it's above 70%, they are in the same cluster, okay? And the question is, can we understand this without doing this actual evaluation of the viewport and measurement of the overlap? So that's the center figure, is what you get if you apply the classical methodology of before, of generating the graph, as explained you, by looking at this geodesic distance of viewport centers. And you see that, for example, this user 24 is no more a single cluster as here. So this one is single cluster. That's why it's a black spot. But is associated to these guys, that even if they're far away, they most likely look at the same direction. So the point projection on the point cloud would be the same. And similarly here, these people are not associated to the same cluster. And that's, of course, because you are in the 6 degree of freedom, no more on 3. So you cannot only rely on one metric. And the same is if you rely only on the physical position on the space, that will not really be representative enough. So we have developed new metrics. That was already a partial result. We have now improved it further, that kind of take a consideration more information, so both user position and viewport center and pairwise distance in that sense. and try to and is able to identify clusters that are more meaningful related to the ground truth. For example, this black single user is here as in the ground truth, and these people are also here is the ground truth. Of course, it's not perfect. For example, these are all in one cluster, even if it's not the case. So we have improving that in the final version. But that's just to give you a hint on how the current studies of 3 degrees of freedom translates in the case of 6 degrees of freedom. So basically, that's the very first step that we took, and now we have kind of formalized it more. Let me conclude the first topic on user behavior analysis with telling you that we also look at the intra-user behavior. So that's a little bit less graph-oriented, let's say. So there is no graph, there is no clustering. I will not give you the details because I want to focus more on the second part of graph-based point cloud processing. But I found it very interesting because we use information theory measurement, such as entropy and actual entropy. And you don't need to understand exactly what's happening here, but if here you see all the user, and these bar plots are the actual entropy, if you assume that a low value is mainly showing kind of low interactivity level and high entropy level is showing more randomness, this is why it's also higher entropy, it shows more hectic and interactive movements. What is interesting is that some user, even if each of these is the same user but for different videos, they all tend to have low entropy or high, medium, high level of entropy. So that's what kind of made us think that maybe there is a concept of profiling of the user. So some users tend to behave similarly despite the content. Of course, it's not that they completely ignore the content, but maybe some users tend to always follow the main subject, some others tend to not. And these type of behavior are really important if you want, for example, improve predictions or other type of understanding of the user that you would like to perform. So that concludes the first part of the topic, and the second is actually a little bit shorter. So let me tell you that as a summary, the question we try to understand is, do users interact in similar ways? We have shown that with graphs, you can capture user similarity. At least we try to provide a way to do it. And then with that, you can have graph-based clustering to try to understand relevant and reliable clustering for user watching at the same content. After that, we kind of develop a quantified affinity matrix for us to understand the level of affinity between users. And then we also have some use case studies in our work to show, for example, how this information, this affinity can help for example, at the main server, if you prepare your encoding of the representation for Dash streaming, for example, and how that can save you storage time, and similar consideration on what is the gain in the actual pipeline. Then one thing that it's mainly, I put it as a reference for those that are interested, there is also an analysis that is more looking at the single user behavior and kind of whether that can be considered as profiling, so whether users do have similar behavior despite the content. With that, I hope everything it's clear so far, and you're still with me. So let me go to the second topic, that is graph-based point cloud prediction. So as I told you before, the second challenge that you have or at least another key challenge that you have with this immersive communication is you have completely new format. So you have spherical one with already many challenges behind, by the way, but you also have volumetric content. And that's the second aspect on which we focus. So we mainly focus on point clouds. And the question is, how do we learn representation? How do we represent dynamic point clouds? Why it is important? So let me motivate you a little bit more. And also, can graph help us in this? So a quick introduction for those that are less familiar with point clouds. Point clouds is a set of points that are in a 3D space. So each point is represented by an X, Y, zeta coordinate in the 3D space. It might also be represented by RGB color features. And you have point K, for example, represented by these coordinates, and point I represented by these other three coordinates. They are very typical output of LiDAR sensors, for example. They are highly flexible, can be also good at high spatial resolution. The drawback is that it's an unordered set of points, which means that if I give you PI and PK, and I give you PK and PI, the order doesn't matter, because they will anyway be representing that specific point in the 3D space. So whether I give you these points in a different order, it will still give you the same point cloud. And that's very difficult when you then want to have point-to-point correspondence across point clouds. So Y-graph can helpful for trying to advance these challenges or these problems. Well, as you can see, and as colleagues of us has considered a while back, each set of points can be seen as a node on a graph, and the signal on the graph can be the 3D coordinates or the color coordinates or both. So how that can help us? Let me say that there is an entire field of graph signal processing tools applied to geometric data. So if you see the 3D space as sampled in, for example, 3D point clouds and what we are actually focusing on, so dynamic point clouds, so 3D point clouds over time, you can actually consider that similarly, there is a manifold, a continuous manifold, and there is some discrete graph operators and tools from graph signal processing can be used to process this for the dynamic point clouds. I recommend this very good overview for those that would like to read more on what has been done in this field. I can tell you that there are many tasks that have been considered already, somehow graph related, so both in the synthesis and in the analysis. So point cloud or content segmentation, classification, detection, but also generation, so the synthesis, generation of shapes or meshes. In our case, however, we do none of that. We are focusing on prediction. So can we predict the movement of a point cloud? So if I got the first frames, can I predict what's next? That's our goal. And why we wanted to do that? Well, we started with an idea of encoder and decoder that now do use more and more generative models, deep learning models. So if at the decoder we could have such predictor that could already infer PT plus 1, so the point cloud at the given time, then the sender should only be the difference, not between the PT and PT plus 1, but only the difference between the predicted PT plus 1 and the ground truth, right? So that will be only the content that the encoder should be sending. So that's the first intuition of why we try to look at that. And let me tell you why it is difficult. Well, in an ideal world, you would have 2 points. You would know this correspondence from points over time. You would maybe measure the motion vector. So this point moved in this direction to arrive here in the next time frame. And that would allow you to understand maybe the future movement, right? You could process a little bit more, but it would be fine. And then, however, in practice, that's not really the case. So we do have that this point might correspond to multiple points. We don't know yet a priori how to do it. So we do not have this associated. We can search for it, maybe in this neighborhood, but how? The first intuition is you can do it geographically. So to say, let me find in this previous point clouds all the points that were in the same x, y, zeta space, right? That might be tricky because when you look at movement, if you look at this movement of this person, this is a time t, this is t plus 1, you see, if I want this point and I want to look on where this point was here, I look for a neighborhood that is this sphere here. And maybe I only consider this point, but this point is the right leg, not the left leg, right? It was just close by because it was moving in that moment, right? However, the movement of the right leg that is moving is completely different compared to the movement of the left one that in that moment is the static one, right? So getting this associated to this point, it can mess up completely your predictor. So what we consider is we have a point cloud. We consider a simple K&N graph in which points that are close by in the space will be connected. We use that as an input to a GNN network that extracts features, topological information related to the position and the geometry of these points. And with that, we then build a K&N graph based on the features, which translates, in the fact that, for example, points that are in the yellow leg would never be associated with points that are in the red leg. So you want a neighbor that is more capturing semantic information of the point cloud, not only position and geometrical information of the point clouds. We do this in this cell of RNN. So basically, I will show you now the big predictor picture before concluding. But if you have a point, we kind of build this spatio-temporal graph. So we look at points that are in the same semantic neighborhood in the current point cloud and in the previous one. And then we process that with the classical operator that is used in neural network. And then we extract the state of the point that somehow relates to the information of the movement of the user. So that's to give you an idea on the key aspects that we propose, but this is the big picture. So we want a point cloud predictor, we want a dynamic structure, and a point cloud reconstruction. So the structure does take the 3D points and endpoints with the 3D coordinates. It extracts the features, and it builds this new graph based on these semantic features. It then processed by a graph RNN cell that, exploiting the spatial-temporal graph or correlation, is able to extract the states of each point. It is processed actually by a concatenation of RNN cells, and then with the fully connected layer, it extracts the motion vector. So this is the motion vector, and then taking the previous point clouds plus the motion vector, we predict the next one. So I will skip the details as we don't have too much time, but here is the body's point cloud that we created with Maximamo Adobe tools. And this is the prediction that I showed you before. That is the result we get. So the network is able to capture the movement. We still suffer quite a lot about deformation. So as a future work now, we would like to better understand how to correct this deformation. And of course, exploiting graph constraints could be a solution. So that's to conclude the last block of this talk about dynamic point cloud predictions, in which we shows how to extract dynamic features by GNN networks and how to use spatial temporal graph to extract point states that can be translated into motion vector. Let me conclude with some future works and open challenges. For the first part, mainly, we do have still a lot to do in terms of how the analysis can then improve the user-centric system. So many application encoding, quality, streaming, and etc. So we are now looking at how can improve prediction, but of course there is a plethora of information and steps that can be done. And I didn't mention because we don't have time, but there are quite some works that try to use graph in better processing spherical content. Sorry, in improving the prediction. And that's something that can then be used to improve the overall pipeline. One thing that I have to mention is that at the moment, most of the work use bits and there to improve coding, prediction, adaptation logic, while I think it's still missing an end-to-end optimization that, for example, improves the tile design, given the user behavior and given the adaptation logic, and try to really see it as a whole to really maximize the gain that you can get. Graphs, of course, are highly useful also because of the fact that you are looking now at spherical content, and therefore spherical processing can be beneficial. Big challenge is also how you can translate this into different applications that I mentioned before. That's something that we would like to dig deeper if possible. In terms of point clouds, there are many open challenges. For sure, the aspect of dynamic point clouds is a little bit less investigated than static one. So how that can be improved, how that can be translated into actual compression techniques. There is in the computer vision field some very interesting work that try to look at skeletons, so key structure of the point cloud, how that can be then also used in dynamic point cloud feature extraction is also another very interesting bit. And for those that are also less media related, I found this very interesting anyway, because we still believe that this study is a more study of learning dynamic features from a set of points that live on irregular domains. We see the application as point clouds, but can also be any type of dynamics point. So social networks, traffic management, and other. So I don't have too much time to talk about that now, but we have a parallel field of research that try to also look at that. So graph-based dynamic processing or large-scale networks. These are two examples of how we use it to improve recommendation systems, or how can we have influence maximization. So how can we understand diffusion of information on large-scale networks? How can we manage that? How can we optimize advertisement places in a social network, given the dynamic of the social network, in such a way that then we can maximize the profit, for example, or the click probability. So there is an entire field of graph-based learning that can be used to such an application. With that, I'm already over time, so I conclude. And I'm here for any question, and let me thank you for listening.
Hi, Laura. Thank you so much for the talk. It was very inspiring.
Hi, Alan. Thanks.
Roberto is coming back. I don't know. Maybe he has a problem.
Can you hear me? I'm here.
I just can see you.
You can't see me, but I'm here. Supposed to be here.
You're magic, Roberto.
Restart the camera. I can also see myself in the streaming. But
okay. Maybe it's
anyway,
a problem on me. Roberto, I can pass the speaking for you. You can make the first question.
Okay. First of all, thanks, Laura, for coming. It's always nice to hear you. A lot of nice work. Overall, I think the talk was very enlightening. And yeah, I agree with you that we have this web media community, and a lot of the graph part is probably very, very useful also for the web community. And we also have a lot of people working on multimedia, both 360 and I've seen less point clouds, but maybe next year we have more. And yeah, so we have I'll probably start with the questions from the audience. We have one from Deborah Mushalat Saad. So she says, Laura, amazing work, congratulations, and thank you for your talk. Considering a multi-user environment, virtual reality environment, where users would be able to interact with each other, have you thought about how to use your graph model on it, and what you you need to extend it somehow? For instance, when two users, it's a bit, when two users are talking to each other, they are looking at opposite directions, right? So, have you thought about how to extend your model?
So very interesting question. I might say that we have a first work in a social VR experiment that is this year MMV. In case you would like to check, and thanks, because the question is very interesting. So in that sense, I think you may not necessarily change the procedure, because you can see nodes as the different users, and even if they're looking at different directions, that's all the point. It's you have to be good in understanding how to define users that are neighbors. So it's not maybe looking at different directions, but in that case, for example, more to have an interaction network, right? So you would like to build edges for users that do interact between themselves. And one thing that is useful is that you can also have multi-layer networks. So you can have one graph that captures this interaction, so kind of user-to-user interaction network. But then you can also have a graph that captures where each user is looking at, and you can merge these two information together if you want to have something that is kind of taking both into account. Or you can only look at one or the other, depending on what you want to do. If you want to measure interaction between users, you can only look maybe at the user-to-user interaction network or graph. If you want to to look both at that, but also the similarity, maybe if they both go around and wander. You can also look at these multiple levels. We had an initial works about social VR. So there you can see, we actually saw that different type of scenes at different contexts and completely different behaviors, and we try to capture that. But let's say that's a short answer for the moment.
Yeah, I agree that it's a really nice question. And then one from myself, do you think we can actually use this kind of thing to predict the other user interaction? So if you
the answer is that I will tell you in a few months, because we are looking at that now with some students. What I think you can do is to understand if it's a lost cause, the prediction or not, for example. So you can understand if users are really too eclectic in their movement. There is no point of even trying the prediction. One other thing that I really feel is now you train this model of prediction with all users together, but that somehow contains also user that I show you that there are profiling users. So some user look at completely random parts of the content, and having also this type of user in the training set can kind of make it more difficult, the training. So I think you can have some improvement in that sense, either because you select properly your data set, and also the moment in time maybe where you have a chance of prediction or there is not even point in trying. So in that type of sense, I think it can help.
Laura, I have a question here from the audience that Professor Leonardo is congratulating on your presentation. And he asked something that I also interested. He asked about what's the future directions in recommendations, recommendations that you point a little bit in the presentation.
Yes. Yeah.
And he asked if you can explain a little bit of that. And my question is also in this way. In your recommendation series, we saw a lot of matrix factorization, right? There's a lot of planar data that you use it to recommend user recommend system. How do you see that? Just increasing his question, right? How do you see that this graphing signal processing can help in the recommendation?
Yeah. So thanks very much, and I'm sorry I could not really talk too much about that. First, I think there is a lot of future direction in that field. We have now a project with BBC to really try to see the recommendation in the iPlayer and their tool, and we understand that the problematics are really many. So there are already some direction toward matrix factorization. Some work try to show that graph can help in this factorization and this simplification, mainly because you kind of try to construct graph user, item graph, and try to use this topological information to improve the missing information in terms of what could be recommended. The type that work that we are looking at, where we started to look at, because it's really a starting point, is first, it's not very clear how to build the graph. What is the most interesting graph? Is it the user graph? Is it the bipartite graph between user and items in the recommendation? And also, there is another aspect that usually is not really considered, is the popularity of items and the dynamic process of all the items in the recommendation. So I think there are many aspects. One is the methodological aspect on graph to improve bandit, matrix factorization, and some classical methods that are used for recommendations. In practice, when you work with people that really have to do it in practice, you see that there are also many problems that comes from the daily works on. There is dynamics that are not always taken into account. There are video popularity, season trends, and all this kind of extra information that it's also not very clear how to process. And also we're looking at the problem of explainability and safety and privacy. So I see that many people actually would like to understand what is really capture attention in the recommendation to then provide better catalogs. And also what is the privacy related to recommendation. That aspect, I think it's really a completely open problem.
Yeah, I think we already discussed something about that. The graph can be more explainable in some way than a matrix factorization that you just put the numbers there and
Exactly.
You receive the recommendation output.
And exactly, it really can show you the key links that allows the recommendation. So then maybe you really understand the key features that you want to have from video in the catalog or anything that you can have. So it is much more explainable in that sense.
We have another question here about Pedro Almeida. Congratulations on the work, very interested. And he has something about which are the applications of the point cloud vector expedition. Perhaps it can be used for encoding. What do you think about it can be used?
So I think there are two main directions. One is more in the computer vision and graphics. That is still kind of a method that we use to extract features. So it can still be used to detect some dynamic movements or action recognition. While I think also for this type of community, the second aspect is the encoding. It's really interesting. Is what we thought as a first idea. So if you need to encode, but you know that you have a predictor at the decoder side, then maybe you only encode the delta between the predicted point cloud and the ground truth. So you could have these, now there is a lot of encoder and decoder. The generative deep learning models are used in the classical co-encoder now. They're trying to look at that, NVIDIA and many other people. So the question is, maybe could you do the same for point cloud? Yeah. In the encoder, it's an example that at least is why we started this at the very beginning, to see if we can improve the encoder bit.
I have another question. It's more an open question.
Yes.
It's similar that Robert told us. We have few works yet in point cloud in WebMedia, and we have a lot of here experience in this matrix data, right? For coding using CNN and convolutional convolutional operation, and this we are very used to planar data, but you are bringing now these new challenges. What do you think is the key difficulties to coming from this planar words to more a graphical and even and new formats that you mentioned about the spherical one, because we are very using, especially in machine learning as well, with the CNNs and everything.
So it means like for people coming from more the 2D regular domain, what is the main challenge? Exactly. Well, if you ask me, not that much.
No, can I just add something? So what do you think are the practical challenges in the sense of I don't know, we need more hardware support, or we need more we need some kind of hardware support that we don't have now to make things faster, or because all the graphic cards we have now are optimized for these matrix operations, right? That's
so that's a very good question. I think we need so first methodologically wise, it's a much more recent field, and that means that there are still many things that we don't understand compared to CNN and other type of deep learning. So for example, how we really have recursive network in graph, we are still not fully there. So we still kind of process this at the point-to-point level, looking at some topological information, but we cannot still really look at the entire graph and process that as an RNN, for example. So I think on the one side, it's really the understanding on how it works and some challenges. For example, if you have many layers in the GCN, you tend to over smooth the signal. So that's very good if you have global information that you want to understand. But if you want to keep some local information, that's difficult to capture. So I think in computer vision and NLP, we do have now strong methodologies developed by CNN, LSTM, and that kind of field. We are not there yet with the graph geometric deep learning field, let's say. So it's part of what a lot of research has been focused on. Even generative model, it's a little bit, we don't, even what I show you, it's a generative model, it's RNN based, but it's not at the level of results and understanding that we have for the 2D part. And that, I think, the processing also is one, because the why we don't have that is because we cannot take the whole graph and process it all together. So one is the computational, the processing needs that we still lack, especially because we don't want always to have Laplacians and inversion of Laplacian and operations that can be very difficult. At the same time, methodologically wise, there is still a lot of research to be done, at least if you ask me, to reach the level of CNN, LSTM, GANs, and others.
Yeah, it's a completely new world, right?
Yeah.
Laura, there is a question from Tiago. Tiago asked a little bit about more the analysis, the user analysis in ODP content, and he asking about the how much it can be applied in online, like in real time systems can be make some profiling and some prediction. I think you have a lot of things to speak about that.
Yeah, so we'll try to give a short answer because I know we are running out of time, but a very interesting question. So the profiling is mainly an aspect of why we wanted to try to do that, to really, in the online, I think the most difficult part is which information do you need. So the one in which you only have one single user information, like the profiling, it can be physically done online. The inter-user information can be done live with the metrics that we consider. That's only viewport centers. That's why we wanted to do it, because it's really simple. You just look at, while you capture the information, you can predict it. And we have this sliding window, so you can do it over time. So that's totally feasible. Of course, the more complicated is the metric that you use, the less is feasible to be done live.
Laura, I think we passed our time. I think we can be more time here.
I gave a short question. Sorry about that. I took too much time with the presentation. I knew.
No, I think we are supposed to end right now. We passed some minutes from the deadline.
Yeah.
I'm just would like to thank you so much for your time.
Thanks for the invitation.
I know you have a very tight schedule. So you can say some words just to the audience.
Yeah, no, first, thanks, because I got very interesting questions. For any question that we could not address here, of course, I'm reachable by email or by Alan and any other ways. And I'm very happy to discuss more about research as of course you can imagine. So thanks again for listening.
Thank you.
Thanks a lot, Laura. I actually have a lot of questions, but more discussion, but we can do it later.
We can have a chat. Yes, Roberto. Thank you.
Yeah.
Bye.
Thanks a lot for. Yeah.
Okay, everyone. I will finish the keynote here. I really appreciate the questions and everything. So hope you guys have a good day. We'll have some technical sessions after. So enjoy the WebMedia. It has been amazing event this year. So bye everyone. Bye Roberto. Thank you.
Bye guys.